Welcome, everyone, to today's webinar hosted by the Institute of Navigation on the topic of commercial GNSS radio occultation on aerial platforms with off-the-shelf receivers, published in the winter 2022 issue of Navigation, the Journal of the Institute of Navigation. Today's webinar is being presented by one of the paper's authors, Brian Chan. Brian Chan is co-founder and CEO of Night Crew Labs, where he conducts research on GPS radio occultation methods on aerial platforms. He has over a decade of experience in the aerospace industry, spanning technical roles in government organizations to executive leadership positions at startup companies. He's also a co-founder at Zona Space Systems and is the VP of Business Development there. He received his BS in Aerospace Engineering at Georgia Institute of Technology and his MS degree in Aerospace Engineering at Stanford University. You can download the full technical paper plus many more on the Navigation Open Access website at navi.ion.org. The site has tools that allow you to read, download, cite, and share valuable research content such as this paper. So thank you for being here, and now we'll turn it over to Brian. At the end of his presentation, you'll have the ability to ask questions using the Q&A portal. Take it away, Brian.
Okay, wonderful. Thanks for that introduction. I really appreciate that. Appreciate your invitation to speak today, and of course, all the attendees that are listening in. So yeah, good morning and good afternoon. My name is Brian Chan. I'm the president and co-founder of Night Crew Labs. We'll talk a little bit about our research here. So try to get the next chart here. Yep. So outline a little bit about Night Crew Labs, our motivations to do this research, what this all generally means for society, and then a little bit more into the engineering aspects, the instrumentation of our payload, how it was designed, how it was developed, the kind of accommodating bus system surrounding it, and more detail on some of the flight platforms, and of course the results. So Night Crew Labs is an engineering technologies company. We're based in the San Francisco Bay Area, have a team of researchers and industry professionals. Our strengths include GNSS research and high altitude ballooning. And our mission is really to harness the power of high altitude platforms, revealing insights about the natural world. And the research that I'm presenting and talking about is this GNSS radio occultation hosted payload for aerial platforms. So, why does this matter? So before getting into the nitty-gritty here, the real motivation is really about our changing world, and weather events are becoming more and more unpredictable and damaging than ever. Did a quick digging on last year. NOAA actually just issued this, came out with a report on these billion-dollar disasters. So just last year, there were 18 of them, 3 of which were tropical cyclones, Fiona, Ian, and Nicole. So if you lived on the eastern seaboard, or certainly Florida was directly impacted by some of these tropical storms. And so 3 of 18 doesn't sound all that much, but when you look at the dollars and cents of it, the chart at the bottom right there, you can see that they're extremely severe. So if you compare the plot to the right or the bottom here is in kind of this orangey, dark orange brown is the dollars and damages associated with all these, the 3 tropical cyclones at the very right-hand side. And then everything else, flooding, droughts, wildfire, all that's all those dollars and cents are close to the bottom, in gray and magenta and blue. So, and this is not unique for 2022, as you see, as you keep going down in years past, there is very severe hurricanes, like Hurricane Sandy, for example. It was that big spike in 2012. The list goes on. So clearly this is a really big issue for not only for the United States, this is just the US, but obviously the world. And so, understanding as much as we can about hurricanes, hurricane intensity, forecasting where they'll be going, right? This is still it's not a solved problem by any means. And so obviously a lot of folks are doing a lot of good things right now and with our weather sensing tools, but it behooves us to really take it a step further and see if we can resolve these forecasting methods even more. So, while that's happening, another aspect of this is, weather data is transitioning from, only government type data collection systems to commercial data providers. And so this is where GNSS radio occultation comes in, where, today there are government folks and government-based satellite systems performing this, but it's also moving to commercial operators. And yeah, space-based operators are delivering commercial weather data today to help with weather prediction, but most notably tropical cyclone forecasting. So, what is GNSS radio occultation, and why is it good, and why does it help with tropical cyclone forecasting and predictions? Well, it's a remote sensing technique that really leverages the signals coming from GNSS. So if you look at the graphic on the top right there, the way it works is basically, the GNSS satellite broadcasts satellites, right? Or sorry, signals that folks use for positioning normally. If you are an observer, or if you're a sensor kind of on almost the other side of Earth, that signal has to pass through the atmosphere, which has water vapor in it. And that signal gets measurably bent, and the signal gets delayed. And so if you're an observer and you have a clock, you can actually measure how much that signal is bent based on how long it took that signal to get to you. And so this is the analogy I'd like to make is the whole, with a straw in a glass of water, right? The straw is bent, or it looks a little different, right, when it actually hits the water. And so that's essentially what that is measuring the bend of the signal, or of the straw in this case, because of the presence of water in the medium. And so by doing this and doing this kind of globally, you can, with this technique, can resolve atmospheric refractivity, temperature, and of course water vapor, and that's all kind of used as inputs into these numerical weather prediction models. So this is all well and good. Again, space-based ROs are demonstrating operational success, but there continue to be unmet needs, and really require more observational platforms. For example, gaps in very particular areas or specific regions is really important. There's difficulty in tracking that signal as low as possible to the surface, and cost effectivity of the data themselves. And so we're, through this research, addressing some of these needs by leveraging, aerial platforms along with commercial off-the-shelf receiver equipment to effectively, demonstrate that we can do this at scale at low cost. The graphic on the bottom right there shows a global heat map of aircraft flights back in 2019. And I'm really just showing that to say, hey, if we had RO receivers on these airplanes, that sure covers a whole lot of ground, including the United States and around the Eastern Seaboard. And it turns out, actually, I guess part of some of the punchline here is, turns out that airplanes are flying GNSS RO receivers already, in the sense that they're just GPS receivers that need to be changed with a little bit of firmware, and all of a sudden you can get some interesting output out of that. Okay, so what did we do? I'll say that this work that we did represents a culmination of effort starting from 2018 to effectively now, and then really wrapping all that work up. So we started with instrumentation of a payload. We started with a larger form factor, some power or user equipment that took up a lot of power, for example, and then I've worked to miniaturize that down. And so what you see there on the bottom left is a small kind of Raspberry Pi computer with a GNSS chip on it that is suited for radio occultation applications. So we did that. We then looked at different flight opportunities and actually flew these payloads on high altitude balloon as well as various aircraft, collected that data, and then analyzed that data. In this case, the technical term is retrieved refractivity and kind of interesting atmospheric data, and then compare that data to the state of the art, or the what is well established, and to make some conclusions about the data quality and whether it's viable. Okay, so a little bit about our instrumentation. So again, this is this particular payload was for airborne applications. It's basically fit in a rack, like a server rack that folks were flying in this particular scenario. Really, the purpose was of this payload was to, number one, log the receiver's position very accurately. That's a requirement for this technique. And then the second part is actually collecting raw phase measurements of GNSS satellites. The equipment list is there. I'm not going to go through all of that, but in general, we're looking at, or we hosted several different commercial off-the-shelf receivers, configure them in different ways, and effectively, compare the results from all of them. There's other equipment like RF splitters, switches, data logging, power boards and such to make this all happen. So here's a quick look at some of the bus instrumentation. So depending on the platform that we flew on, it required different sets of, let's call them, just payload accommodation systems. So in this case, this was a balloon instrument, and in that flight scenario, it gets really cold, right? So you want to keep the electronics, you want to keep the batteries warm. So we had patch heaters, for example, for that. We had a satellite modem connected to that, so every now and then we could we get telemetry from the payload as it was in flight. We could command certain things and so on. So yeah, it was a lot of I'd say fun engineering to accommodate the payload for the particular flight scenario. And here's just a screenshot of the ground station of that we so this is a Chrome-based or web-based ground station where essentially we could control and get telemetry and data from the payload as it was in flight, and we could just do this online as long as we had an internet connection. And so there's we had an overlay map on there. You could see the ground track as it was in flight. There's temperatures that we're showing. We could just make sure that things weren't getting too hot or too cold. We could turn things on, we could turn things off. We could change the altitude of the balloon to some extent by dropping ballast mass. So yeah, there were a number of interesting and useful features that were part of all this. And then it was really important when we're talking about longer flight times of hours or even days aloft. So just to talk a little bit about some of the flight platforms that we did fly on. So on the aircraft side, there were two that we flew on. One was the King Air research aircraft. This was through the University of Wyoming. So it's a prop plane. It's fairly small, as you can see in the top right there. That's the inside. Basically, they gutted the inside, so there was really just the pilot seat and two small seats for scientists and researchers. Everything else was just research equipment. And so that got a little bit claustrophobic, but it was definitely fun. And we flew in the winter time of Wyoming, so a lot of kind of beautiful snowy scenery over there. A little lower altitude being about 20,000 feet or so. And then the bottom, we flew on the NASA DC-8 aircraft. So this was considerably larger aircraft. So this was kind of a 727 or 737 type size aircraft. So much larger, but kind of a similar situation inside, where they had a lot of server racks and kind of instrumentation and power hookups. And also, I'll point out the engineering side of me likes to point this out, where with the DC-8 aircraft, they had their own SATCOM link, right? And they had their own power and all this. So it was actually a bit easier, let's say, to interface with the DC-8, because we could use some of their resources on board. Compare that to the balloon platform, it's a little bit different, right? So we flew on 2 major campaigns. The first one was a super pressure balloon mission or flight through Worldview Enterprises out in Tucson, Arizona. They flew a multi-day mission with their platform called the Stratolite. So on the top right is basically a pyramid-looking, shaped-looking platform, where again they had a number of other payloads. You can see they had a ladder of solar panels, so that's just prior to launch, and then our payload was basically within the container there, and then we had our antennas out to the sides. And then the bottom there is our own, the Nitro Lab Zero Pressure Balloon flight, where we basically, short of actually building the balloon, we basically did everything, where we designed the payload. We basically stuck it in a styrofoam box. Turns out that's actually really good for this kind of application, right? Very lightweight, but thermally insulative. Filled it, launched it, recovered it. And that was a 12-hour flight. So just a few pictures. This was part of the hardware stack. In fact, this was this particular one we worked with University of Colorado Boulder for them to fly one of their payloads, actually. So this was a pretty heavy duty one there, SDR based receiver. This is an aerial shot of, as we're setting up. This was out of Nevada, Empire, Nevada. If you've ever been out there, it's just about in the middle of nowhere, right around Black Rock Desert or so. This was a few minutes before launch, nice and sunny, very low wind, which was great, and effectively filling helium from the back of the truck there. This was right after launch. The whole kind of, once we actually got to the site, I'd say the setup, launching, doing various checks and things, that took about an hour and a half, maybe 2 hours or so, just to make sure everything was working. Because once you launch it, you can't really take it back. This was a photo from the payload just a few minutes prior to, or right after launch, of Black Rock Desert. This is the recovery and just all of our stuff to make that happen. And then this was a mosaic or a composite picture of Nevada at about 100,000 feet, or about 30 or so kilometers in altitude. This was the flight path from Empire, Nevada, flew across state lines over to southern Utah. Okay, so that was just some photos from that flight back in 2020. There were many other flights and flight campaigns over the years. These are really the ones that I had talked about on some previous charts. I'll mention that we flew twice with the NASA DC-8 aircraft. One was out of St. Croix, U.S. Virgin Islands. The other, it was both Jacksonville, Florida, but also Cape Verde, over off the coast of Africa. And so, as you noticed, in September timeframe is hurricane season. So we actually were able to collect some interesting and good data right around, tropical storms. I forget, I don't want to misspeak on which hurricane we flew right next to, but that was back in 2021 for that particular time. But as you can see, just very different flight conditions, different atmospheric conditions, right? If like tropical, heavy humidity weather versus say, much drier, cold weather in Wyoming. We were really just trying to sample as many kinds of scenarios as possible and kind of test the rigor of our setup and just really just see how it performs over different conditions. Yeah, so I think before getting even into the quality side of things, I think it's important to talk about the quantity aspect of it. So, with a balloon, there's various things you can do to actually station keep over a certain area. You have to kind of do some wind sailing, if you will. And so the graphic on the left in red is the balloon trajectory over 5 days. And then these in blue are really all the observed GNSS RO events that happened over the 5-day period, which is a lot, right? There's very high density of RO. In fact, that believe it might be one of the highest densities that anyone has shown just by nature of this station keeping ability. If you compare that to what's happening today with about tens of satellites or so that are collecting GNSS RO measurements all across the world, if you look to the right here, it's certainly very impressive, right? The global span of all these collections. However, I'd say if you really zoom in on say in this particular area over Arizona, the number of ROs becomes much more sparse, and so by comparing the two, we've really shown that a single balloon flight has demonstrated over 6.5 times more RO density than all the space-based ROs combined. And this is particularly important when you care about certain regions, such as again the the eastern seaboard, or when a hurricane is incoming. You really care about those data points much more than you would say ROs over say Antarctica or something, or over the North Pole, right? Though those are a bit less valuable than the ones where an impending storm is coming through. And so a little bit about the data that we actually collected themselves. So to the left and to the right, so based on the collection of raw GNSS measurements, we go through what's called a retrieval process, just a number of kind of algorithms to convert that into bending angle. So this again is the actual bend of the GNSS signal through the atmosphere. And then a related parameter is the refractivity. It's effectively a proxy for water vapor. And so on the right there, you can see the refractivity change as you get closer and closer to the surface. Yeah, we did that. We compared that with these standard what's called ERA5 models. So this is weather data that's collected and output from a ECMWF, which is the kind of the Europe's equivalent of NOAA, their weather agency there. And so they match quite well. In general, we found that balloon-borne data was found to be high quality. We believe that that's true because the balloon platform was much more quiet. There wasn't as much kind of rocking around, and there wasn't an engine on board, right? That caused a lot of vibration, things like that. And I think also by nature of being a little bit higher helps out with that as well. And then I think this might be my last chart here, just more analysis and showing that, yeah, we're actually very close to standard models. And so, in general, we tried 2 different retrieval models. You can see one on the left, it's called Geometric Optic, one on the right called FSI. And in general, right, like we're trying to get that median line, that blue line, to be as close to the center as possible. That if it was directly on 0, that would mean there's no bias. It agrees completely well with the models that are out there now. And so you can see that they match within like 2%, but well within 5%, which is the general agreed upon standard. And I will say that it gets a little tricky too, right? Because the model that we're comparing to is also the model that we're looking to improve, right? And so it wouldn't actually make sense if we were totally like bang on at zero. We're actually believe that there is value there, right? And we're actually showing that, or improving the model itself in particular regimes. So this is kind of a constant area of research, not only for us, but in general to the atmospheric community at large. But yeah, I mean, we believe this is really valuable information and kind of data that we've analyzed. And so, what does this kind of all mean? And to really wrap things up here, we, through all this work, demonstrating that meaningful scientific data can be retrieved from airborne platforms using COTS components. We've demonstrated that a balloon system can collect a unprecedented density of this type of data over a particular region. And our research believe that it paves the way for these kind of high volume, low cost data sensing techniques to take place at scale. So yeah, thank you to our partners at NOAA, at NASA, some of our academic partners like Texas A&M, Corpus Christi, and at the bottom there, just a plug at our navigation publication that was released in the winter edition for 2022. So yeah, with that, I appreciate your time. Thanks for listening, and happy to open up to any comments or questions.
Thanks so much, Brian. We appreciate this great webinar. If you have a question for Brian, you can enter it using the Q&A tab in your viewer. We'll pause for just a minute to allow viewers to enter their questions. So Brian, while we're waiting, I do have just a couple of questions from your presentation. And keep in mind, I'm not an engineer. I don't play one on TV, so this is coming from a civilian. But in general, why are hurricanes so hard to predict in the first place? And how does this technology help with that?
Yeah, it's difficult to predict hurricanes because, well, there's really two types of ways people collect data in general. One is, they call it in situ measurements. So something like, your phone's pressure sensor. Like, so if the actual sensor was there on the ground versus something that's remotely sensed, such as with satellites. In hurricane, when a hurricane comes, generally airplanes and ships get out of the way, for obviously. Turns out that airplanes and ships are actually, they have weather sensors on board and provide information to folks like NOAA. But when a hurricane comes around, since they're going away, there's no in situ data, and so you're left with these remote sensing platforms to do all the heavy lifting for a very potentially severe storm. So really, then the onus goes on the remote sensing and like how much juice we can squeeze out of all these different techniques. And again, this is part of where GNSS RO comes into play. Yes, like satellites definitely help, but the point is, with aircraft or with balloons, you can still sense what's going on in the hurricane, but you don't have to be directly, in the eye of the storm or even terribly close by. And so this is some of the promise that this kind of technology brings. Yeah, hope that helped answer.
Yeah, absolutely. We had a webinar, I guess it was almost 2 years ago, from NOAA hurricane hunters themselves, and talked about how they navigate through the storm. Do they take these types of measurements, or are they looking at other things when they fly through the eye wall and into the eye of the storm?
Yeah, so those storm chasers, they have sensors on the aircraft themselves, but they also have these things called dropsons, where it's basically like a robotic sensing that they just throw out the window. It's probably a little more complicated than that, but as that sensor floats down over parachute down to the surface, they can then pick up some really interesting data to help them out. And it's really all about water vapor, sensing that water vapor and doing so at as low to the service as possible. That's really the key data that is just kind of lacking, or it could be a lot better to improve, forecasting on intensity and where it's going.
Yeah, great. We do have a question here from one of our viewers. He said, did the authors compare RO observations between different GNSS receivers on board, and what was the takeaway?
Yeah, we did. So there were three GNSS receivers that we looked at. One was a Trimble, one was Septentrio, one was SwiftNav. So there were kind of different. There's a lot I can talk about, but in general, what we were interested in was from an engineering or development standpoint, we want to see how modifiable over software some of this user equipment or some of these receivers were. So that, because through this technique, we're trying to track GPS satellites effectively on the horizon, or in fact, even below the horizon. And we actually can do that because the signals do bend. And because of that, we wanted to play around with different tracking parameters, different gains and things like that. And so we found that the more easily we could do that, the better. And so it turns out that in our the specific receivers that we used, the SwiftNav was actually really fairly easy to modify and for this particular application. So I would say we got the most data out of that one, but not to say that the other ones weren't high performing. They did work, obviously, and even with the Trimble, we used that one as our kind of high precision navigation system for us, right? As I mentioned, we really need the balloon, or the aircraft really needs to know how well or how good its position is, so we can even do this measurement in the first place. And so we used that receiver with their corrections service on top of that.
Okay, well, Brian, we see you've got your email address up there, so if someone has a question, they can contact you later. We really appreciate your time in putting this together today. Again, you can read the full technical paper on our website at NAVI, that's navi.ion.org, where you can download, read, cite, and share this article and many others. So, Brian, thanks for your time.
Great, appreciate it. Thanks, guys. Thanks all.
Yep, have a great day. Bye-bye.